So now that we know how to create some simple logic circuits on paper, and we also have a basic idea of how to describe those logic circuits in Vhdl, how do we get that logic circuit onto some actual hardware? So what we're going to do now is figure out how to complete a lab assignment and take your logic circuit that you've designed on paper and get it onto actual hardware. So your Digital Nexus board has what is called an Fpga on the board, and that's the large square chip in the middle. An Fpga stands for a Field Programmable Gate Array, and this consists of a bunch of configurable logic blocks. So as you see in this diagram here, the CLB stands for Configurable Logic Block, and it allows you to configure this chip with any digital logic that you so choose. So you can write any digital circuit and have it work on this chip. So these configurable logic blocks are basically made up of a whole bunch of lookup tables. And the lookup tables are just like a truth table. They tell you what inputs give you what outputs. And so the Fpga is configured so that it figures out, okay, this configurable logic block will have this lookup table, and this configurable logic block might have a different one, and there's all this then routing circuitry in between these blocks in order to see what outputs of one block would connect to inputs of other blocks. So that's basically what we're going to be doing, is we're going to be configuring the Fpga with the appropriate circuit that we want to implement. Okay, so you want to go ahead and open up your Xilinx Project Navigator software, ISE Project Navigator, and mind you, I have version 14.3, so yours might look a bit different. So we're going to go ahead and start a new project. You might have a button that looks like this, New Project, or you might go to File, New Project. But go ahead and click on that. Okay, I'm going to call this Lab 0 because this is going to be an example lab. I would go ahead and create a folder somewhere on your hard drive. I'm going to go ahead and put mine on my desktop. I'm going to make a new folder called CPE 133 Labs. And therefore this folder should be able to contain all the labs I'll create in this class. So I'm going to put it in that folder, and it's going to create a Lab 0 folder within that folder to hold this lab assignment. Okay, so now we're going to go to Next. Now we need to specify the board that we are using. And we are using the Spartan 3E starter board. And as you can see, that'll fill in the rest of this stuff. You have the Spartan 3E chip, which is the Fpga that is on the board. This is the family of the chip, and then this is the actual device. If you remember, when you purchase your Spartan, you could have a 500 or a 1200. That's sort of the size of the number of logic gates. Then this tells you the exact packaging format and the speed. So you can purchase different Fpgas that have different characteristics. We're going to go ahead and use Vhdl in this course. So your preferred language is Vhdl. There are other languages like Verilog, which you could use, but we'll be using Vhdl in this course. And we'll keep the simulator as iSim. And there we go. We're going to click on Next and Finish. Okay, so that brings us to a new project, and you always want to start every digital design with a block diagram. So let's go back to our bacon, ice cream, chocolate example, and let me draw the block diagram for that. We're going to have a black box. We're going to give this thing a name. I think in my example I called it Spoon. And we're going to have 3 inputs, 1, 2, 3, and an output. And my inputs I'm going to label bacon, and ice cream, and chocolate. And my output I'm going to make S for spoon. So there you go, we have our black box diagram for this simple circuit. Always start with a black box, always label every entity, always label every input and every output, because this will help you know what to do. Alright, so we've got our black box for this circuit. I'm going to go ahead and click on this new source wizard. It has a little flashy symbol. And I'm going to pick Vhdl module because we're going to create a new Vhdl module. And you want to give this the name of your circuit. So remember, our circuit is called spoon, so we're going to call this thing spoon. And we're going to click on next. So now it asks you to put in the inputs and the outputs. So again, our handy dandy black box diagram tells us we have bacon, ice cream, and chocolate. So we have a B, an I, and a C, and those are all inputs. And then we have an output S for spoon. So S is an output. Now notice you have this option of having a bus. If you click on that, if you had more than one bit, let's say bacon was a 2-bit thing, then I could say I want a bus that is of size 2, so I would go from the MSB, which is the most significant bit, to the least significant bit of 1 to 0, saying I have a 2-bit option. But we're not there in this first test, so we don't need to worry about the bus. So we have 3 inputs, BIC, and 1 output S. Next. Here we're verifying our stuff that we entered. Very good. And now look at this. We have a lot of stuff already filled in for us. How awesome is that? So now, before you get started on any of the coding, go ahead and enter your information in the header. So Cal Poly, your name, the date's already in there. We're calling this spoon. And all these other things we can just sort of say. Our target device is the Nexus 2. Tool versions. This is a lot of extra information. But give a description. This circuit takes in 3 inputs: bacon, ice cream, and chocolate syrup. And outputs a desire to put the contents on the spoon based on input conditions. I don't know. Some description that tells you what this thing is supposed to do. If you have any dependencies, this means like other files that you might need to include, you can list them here. And then you could add a revision history. So revision 0.01 is we created the file. Then if you go back to your file later on, you could add some revision history. So this is just some information for you to have, practicing good commenting style, and always start by filling that out. Okay, so now we're going to start our code. We can comment on, or rather delete all this stuff. And you can see here we have an entity spoon with our inputs and our output, and then we have an empty architecture. So now we need to enter our architecture. So if you remember, we're going to say S is assigned bacon and not ice cream and not chocolate, or not bacon and ice cream and chocolate, or not bacon and ice cream and not chocolate. End the line with a semicolon. And there we have it. We have our architecture. We've described now what this circuit does. What does it do to the inputs to produce the output? So if you had more than one output, you can list another assignment for the other output or whatever. And there we go. This is a very simple circuit, so that's all it needs to do. So now what do you do? Okay. So as you can see over here, we have our spoon module listed in our list of files. It has this little symbol next to it which means top module, which means that if you had a whole bunch of other files, you would set one of them as the top, as like your overall design file. We'll get more into that as the class goes on. But anyway, so now that we have spoon, what are we going to do with it? Well, with most coding, what you have to do first is check your syntax. So let's click on Spoon. You'll see we have all these processes that come up as options. We're going to go ahead and synthesize. So if you right-click on Synthesize and hit Run, it will start checking the syntax of your code. And not only does it check the syntax of your code, it also goes through your logic and tries to optimize your circuit design. And we will be talking about some optimization techniques later on in this course. So look, we got a green check mark. Yay, that means that our design completed correctly. Now if we had errors, which you are bound to have errors, we'd get some warnings that show up in this console down here. So for example, let's say I didn't have a parenthesis there. Oh, there's an error in the syntax. I click on the error and it will show me exactly where it thinks it is. Now, this synthesizer is not always great at telling you exactly where your errors are, but you know, it does a pretty good job. So it might not always be at the line that it says it is. But in this case I know, oh, I am missing a parenthesis, I'm going to put it back, and then I can re-synthesize. Okay, so if I get my synthesis to complete correctly, I'm going to move on to my next step, which is to test my circuit with a simulator. Simulators are really great because if you are making a more complex circuit, instead of needing the hardware to test it out, you can just test it out in software using a simulator, which saves a lot of time and money. So let's go ahead and create a test bench. So if you click on the new source file, I'm going to select a Vhdl test bench and give it a name. I'm going to call it Spoon Test 1. And we associate this test bench with a certain module. So we're going to associate it with the Spoon module. If we had a list of modules here, we could select from a list of modules here of which one we wanted to test. So we're going to test Spoon. And now we're going to get a file generated for us. Oh, there's a whole bunch of errors already. We'll deal with those in a moment. Okay, so again, the first thing you do is fill out the header file. I'm going to do this fairly quickly. And design name, Spoon Test. And it's the target device of Nexus 2. Tests the Spoon module. And no dependencies, and I'll complete all this. Okay, great. Delete this. Alright, so now we have all this automatically generated code here for us. We've created a Spoon test, and now here's the architecture of Spoon test. So you can see it first starts out by listing a component. We are testing the component Spoon, which is why it's listed here. Then it lists the inputs to this component, bacon, ice cream, and chocolate, and then it lists the outputs, S. Okay, so these signals now allow us to assign different values to the inputs to be able to read an output to test our circuit. Now we're going to go ahead and delete all the stuff associated with the clock because our design has no clock. In the second half of this course, we will be making designs that have clocks, and we will get into that at that point. So for now, we're going to delete the clock. Now it says we're going to instantiate the unit under test, so we're just going to be mapping the inputs BICS to the signals BICS. That's what this does. And again, we're going to get a little bit more into this syntax later on. For now, you can just leave this automatically generated stuff there. We're going to get rid of this whole clock process definition because we don't have a clock. And now we can move on to also getting rid of this clock statement, where the comment says insert stimulus here is where you can start typing. So this is where you give the circuit some stimulus or inputs to test what happens with those inputs on the output. So what I like to do for simple circuits is just put in all possible input combinations to see if I get the output I desire. So I'm going to set B to 0. I'm going to set I to 0, and when I have a single bit, I use the single quote, and I'm going to set C to 0. Bacon, ice cream, and chocolate are 0, and then I'm going to wait for 10 nanoseconds. So for 10 nanoseconds of time, these are the inputs I'm going to have, and hopefully the circuit will give me an output S that will be either a 0 or a 1 depending on what it should be. Now, in our case, we didn't want an output when we had nothing on the spoon, so this should give us an output of a 0. Okay, so then we could go ahead and just copy this and modify it. Now we could have the option where chocolate is a 1 and the others are 0, and you'll see here that we can just create 8 different input combinations. Do 1, 1, do 1, 0, 0, 1, 0, 1, a 1, 1, 0, and a 1, 1, 1. Alright, did I get them all? I hope so. 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I did all input combinations. I'm going to save, Control S, and now what I'm going to do is click on this simulation radio button, and I had done this previously, so I have a spoon test 2 listed, but I'm going to look at spoon test 1. Go ahead and delete this so it doesn't confuse anybody. Spoon test 1, I'm going to click on here and say simulate behavioral model. So I could also first check the syntax, but if I don't double click that, it'll automatically happen by just clicking simulate behavioral model. And so what this is going to do is going to bring up my simulator, which will take my input stimulus and tell me what my output is. Alright, so here it is. You can see we have our inputs and outputs, and I'm going to click on this zoom to full view button. Okay, remember in our code we told it first to wait for 100 nanoseconds, so nothing really happened for the first 100 nanoseconds. So here we are, this is at, I can move my cursor over here, hopefully. Go to 100 nanoseconds, great. Now I can zoom in. Alright, so at 100 nanoseconds, I had said to set my bacon, ice cream, and chocolate to 0, and look at that. At that time, my output is 0. Now after 110 nanoseconds, I set it to equal 0, 0, 1, where I have chocolate on the spoon, and still my output is 0, which is what we wanted. Then we have bacon is 0, ice cream is 1, and chocolate is 0, so our spoon is a 1, which is correct, because we wanted to output a 1 if we had just ice cream. Now we have ice cream and chocolate, so we also output a 1. Now we have just bacon, so we output a 1. Now we have bacon and chocolate, so a 0. Now we have bacon and ice cream, so a 0. And now we have all 3, so a 0. So this circuit works 100% correctly because the output is exactly what we wanted, what we expected from this circuit. So that is awesome. We are done with our simulator. Close that. Yes. Now what do? Okay, so we go back to the implementation. The next thing that we have to do is add a constraints file. So, what is a constraints file? A constraints file is the file that maps inputs and outputs on your Nexus board to these different signal names. Okay, so we really don't have bacon, ice cream, and chocolate to input into our system, but we could use the Nexus board switches. One switch could represent we have bacon, one switch could represent we have ice cream, one switch could represent we have chocolate syrup, and so we can now map these 3 inputs to those specific switches on the Nexus board. So that's what we need to do with the implementation constraints file. So we click on the new wizard or new file button, and we click on implementation constraints file. And I usually call this file constraints. I think I already created one, so I'm going to call it constraints 2. You can give it any name you want. And it's going to be associated with spoon. Another editor is running. Yes, let's go ahead and open the editor. Spoon test 1, constraints. Okay. So, once you have the constraints file, you'll see it listed underneath the spoon. So if you click on the plus arrow, you'll see the constraints file is there. We can now use two methods to create the constraints file. I'm going to go ahead and start with using the tool. So you can use the plan ahead tool, IO pin planning, post synthesis. So you can do this now after synthesis because we've already finished our synthesis. So yes, we're going to use constraints 2. in this program called Plan Ahead. Alright, while that's opening up, I'm going to remind you about this Nexus 2 board pin assignments file that you can click on. And this shows you what the pins are on the Nexus board. So the first switch, we're calling it switch 0, but it has pin location G18. So we'll see how that's used in a moment. Okay, here's our plan ahead file, and let's go ahead and click on our scalar ports. We have bacon, chocolate, ice cream, and spoon. We need to assign it to a specific site. So we're going to make bacon site G18 because that was our switch. Now I'll go back here, we'll make chocolate H18 and ice cream K18. So chocolate will be H18, ice cream will be K18, and now S is an output, so we'll make our output a light emitting diode, an LED. And let's see what's one of those. LEDs, we have LD0, we'll make J14, will be our spoon output, J14. J14. Great. Okay, so now that we've done that, we're going to save. And we can close out of that. Okay, I'm going to get rid of this one. Okay, so now we can see, we can also edit this textually, and that's why this keeps coming up, because you can use that editor, the graphical editor, or you can just use it in the text editor. And so here you can see we've done the same thing. It creates the net B, which is the name of the input, and then it tells you what location it is. So in this case it's location G18, and then we have C is at H18, etc. So if you don't like using the Plan Ahead editor, which was under Tools, Plan Ahead, IO Pin Planning, Post Synthesis, you can just go ahead and follow this same format for all of your inputs and outputs and type it directly into the text editor. And notice this is a comment in the constraints file with the little pound sign. Okay. Now that we have the constraints file, now that we've tested our circuit, we can go ahead and get this puppy ready to put onto our board. So we're going to go back to spoon, and notice we have these next steps to do. Implement design. Let's go ahead and get that started. If you look at implement design by clicking on the plus arrow, you'll see that it has a lot of stuff to do. It first translates, and what that does is it takes the netlist that came from the synthesis part and translates it to the specific technology on your chip. So in our case we have an Fpga that has a certain number of lookup tables, and so it translates this netlist into figuring out how many lookup tables need to be used. Once it figures that out, then it has to map that, which means, okay, which lookup tables are we going to use on this chip? Now that we know how many, which ones are we going to map them to? Okay, now that we know which ones we're going to map them to, where is everything going to get placed and routed so that everything works together? If everything is green, everything is happy, and this is a wonderful story. Okay, so the last part is to generate the programming file. So we're going to double click on that. And this last step, what it's doing is it's taking a design that we have synthesized and implemented, and putting it into a bit stream that we can download to our Nexus board. And once it does that, a bit file is created. So let me navigate now on my desktop to Lab 0. You will see in this folder there is a bit file, spoon.bit, and this is going to be important for the next step. So the next step is to take out your Nexus board and plug it into your computer. So attach the USB cord from your Nexus board to the computer and turn on the board. So there is a switch on the board on one of the corners that you need to do to turn it on. And you'll know your Nexus board is on if you get a little red light. Okay, so once that is plugged in, go ahead and open your Adept software, which is another piece of software you had downloaded. And if everything is corrected just fine, you'll see this screen come up. If something's not working, you'll see something else. Okay, so we're connecting through the onboard USB, and we're going to program our Fpga with the bit file we just created. So we're going to go ahead and browse to where that bit file is. I had it on the desktop in my 133 Labs folder, Lab 0, and there it is, spoon.bit. Okay, and you can always say yes to this. And then once we've added it, you go ahead and program it. And you can just say yes again. And once it's programmed, you can go ahead and test it. So if you go look at your board and start flipping the switches 0, 1, and 2, which is what we programmed for our bacon, chocolate, and ice cream, you can see which combinations will turn on LED 0. And like we did in the simulator, you can go through all possible combinations and make sure that that light just turns on for the ones that it should turn on for. Woo! And that's it. That is the process for getting your design from concept to an actual chip. So let's go through the process once again. You start with your design concept, you come up with your logic equation, you write your Vhdl, you synthesize your Vhdl to make sure that it's all nice and pretty and works with the syntax. Then you test it in a simulator to make sure the output is what you want. Then you add your implementation constraints file so you can map the pins or map the inputs and outputs to actual pin locations on your development board. And then you implement, translate, map, place, and route. You generate your programming file, you open up Digital Adept, and download that file to the board. It is quite a process, but hey, it's come a long way, and it's pretty darn awesome.